Hi, I'm Sang from KAIST. I'm really happy to present our work here. This work has been done in collaboration with KAIST and University at Buffalo SUNY. Then let me start my presentation. Recently, there appeared various surfaces and they become pervasive in our daily life. From smartwatch to smart TV, their surfaces have different size, and a new type of devices are commercialized, such as foldable screen and dual screen. This trend can change the existing paradigm about how to interact with applications. Until now, we have interacted with surface at a time, but in the near future, we can utilize multiple surfaces concurrently. Let me show you one example. Applications which allow users to watch broadcast while chatting with other viewers. But we have often experienced and broadcast windows on the single surface. Then, what if we can deploy the keyboard window to other device? I will show you our demo video for this example. First, a user should be able to select any UI object from target application and then migrate them to a different device like this. After that, this user can enjoy live streaming more conveniently through multi-surface interaction. We can envision many use case scenarios like this example. Of course, there are some existing solutions for multi-surface interaction, like customized apps, screen mirroring, and migration. But they have low applicability, low flexibility, and low responsiveness, so these solutions may limit the potential for multi-surface interaction extremely. So to overcome their limitations, we designed a new multi-device mobile platform which can distribute UI objects to different devices in a flexible, transparent, and responsive manner. It is called Fluid for flexible UI distribution. Our key idea is separation between M-logic and UI parts. Basically, UI objects can dispatch user inputs to M-logic, and then M-logic can update UI objects properly. We extend such behavior to the multi-device environment by separating them. Let me explain more detail. First, a user can select any UI object from target application. After that, Fluid will distribute the target UI to the guest device, and then our wrapper app will draw it on the local surface like this. Second, Fluid provides the same process illusion to both sides. This illusion enables migrated UI objects to M-logic on the host side as if they are in the same process boundary. This design has several strong points. First, it allows users to control multiple surfaces flexibly because a UI object is a fine-grained unit which can make a graphical content on surfaces. Second, our design is transparent to the application layer. So we can support legacy apps without modifying their source codes, and we can develop new multi-surface applications under the single-device programming model. Lastly, our design requires less network transmission because it handles only the target UI object instead of full screen. So now, I will talk about our two main problems and solutions briefly. The first problem is about how to split and distribute UI objects. Basically, Fluid transmits minimum graphical stage needed for UI rendering to reduce network overhead. However, in the case of app-specific custom UIs, it is unknown which graphical states they use. In other words, custom UI class is usually defined by inheriting the existing Android UI class. So some app-specific member fields can be added to its definition. But we cannot identify which member field is used for UI rendering exactly. It's our challenge. So Fluid performs a static code analysis for the target application to identify which member field can be accessed for UI rendering, that is, graphical state candidates. And then, on runtime, Fluid platform can track and transmit the exact graphical state for custom UIs by using the analysis results. The second problem is about how to maintain interaction between M-logic and UI parts. Generally, such interaction is achieved via local function calls. However, these functions cannot be executed across devices fundamentally. So we modified Android virtual machine so that Fluid can transform local function calls into remote procedure calls in a transparent manner. For example, when M-logic invokes a local function of UI object, Fluid can intercept and change this call into RPC message in the virtual machine layer. So when this message is delivered to the guest device, the corresponding function is executed there. For more technical details, please refer to our paper. For evaluation, we implemented a Fluid prototype based on Android Oreo, and we performed some experiment by using 3 device combination with Pixel smartphone and tablet. First, we evaluated Fluid by using 20 legacy applications for 10 interesting multi-surface scenarios like Instagram, eBay, PayPal, and so on. We confirmed that they all use their own custom UIs, and Fluid can support various legacy applications successfully. Also, we checked their UI distribution times are fast enough for interactive use like this. Lastly, we compared network transparent of Fluid and other mirroring techniques under the same multi-surface scenarios. For mirroring techniques, we use Chromecast, which is hardware-based, and Visor, which is software-based. The target scenario is that a user types destination with 11 characters into the search box UI of Naver Map application. Our result shows Chromecast and Visor have dense network transparent, but Fluid has less network transmission like this. Notably, it is interesting to see that Fluid exactly has 11 network peaks during typing time, which correspond to the 11 characters type. It means Fluid can minimize both the amount of data transfer and the number of data round trips by separating M-logic and UI parts clearly. It's our conclusion. We designed and implemented Fluid, which can support a new multi-surface interaction through separation between M-logic and UIs. Lastly, we expect Fluid can accelerate development of creative and useful applications to provide novel user experience. Thank you for listening.